So hello everyone, welcome back to my YouTube channel Hasta Education. So in this video I am going to discuss about the symmetry method to find out the equivalent resistance in a complicated electrical network. Okay, so let's get started. So here it is a complicated electrical network, and let's say all of these resistors have a resistance value of R, and I want to find out the equivalent resistance between these two points. Okay, point A and point B. Okay, and you can note that none of these resistors are neither in parallel nor in series. Okay, so you cannot apply series and parallel method to reduce this circuit. Okay, so what to do in that case? So in that case we can apply symmetry methods. Okay, so let's see how to apply that symmetry method. So to apply that symmetry method, first of all we have to identify the points across which equivalent resistance is to be calculated. Okay, this is the first step. Step number 1, you have to identify the points across which equivalent resistance is to be calculated. Okay, so in that case, so these are the 2 points A and B across which equivalent resistance is to be calculated. Okay, so this is the first step, you have to identify the points. Okay, then step number 2, you have to draw a straight line connecting these 2 points. Okay, so let's say I draw a straight line connecting these 2 points. Okay, so this is the straight line. Okay, this is the step number 2. Okay, then if this straight line divides this entire circuit into 2 equal halves, okay, then in that case we can say that this circuit has first plane of symmetry, or that is also known as the horizontal plane of symmetry, or parallel axis of symmetry, or that is also known as folding symmetry. Okay, so you can see that this straight line divides this entire circuit into 2 equal halves. Okay, the upper half is the mirror image of lower half with respect to this straight line. Okay, so this circuit contains first plane of symmetry. Okay, and if a circuit contains first plane of symmetry or horizontal axis of symmetry, then in that case we can say that the mirror image points are at equal potential, the mirror image branches have same potential difference, and the mirror image branches have same currents flowing through them. All right, these are the 3 conclusion from the first plane of symmetry. Okay, mirror image points. Okay, that means the point which are mirror image with respect to this straight line. Okay, considering this straight line is a mirror, the points which are mirror image of each other with respect to this straight line, they are at equal potential. Okay, so you can say that this point is the mirror image of this point with respect to this straight line, so these 2 points are at same potential. Okay, similarly you can see that this point is the mirror image of this point, so these 2 points are at equal potential. Okay, and the point number 2 says that mirror image branches have same potential difference. Okay, that means the branches which are mirror image of each other with respect to this straight line. Okay, considering this straight line is a mirror. Okay, the branches which are mirror image of each other with respect to this straight line have same potential difference. Okay, you can say that this branch and this branch are mirror image with respect to each other. Okay, so these two, this branch and this branch have equal potential difference and same current flowing through them. Okay, let's say I current flowing through this resistor in this direction, then we can say that same current I flowing through this resistor. Okay, as these 2 resistors are mirror image of each other. Okay, similarly these 2 resistors or these 2 branches are the mirror image of each other with respect to this straight line, so we can say that same current flows through these 2 resistors. Okay, so if small I current flowing through this resistor, then same small I current flowing through this resistor. Okay, And the third point says that the mirror image branches have same current flowing through them and they have same potential difference. Okay, the potential difference across this resistor is equal to the potential difference across this resistor. Okay, as these two resistors are mirror image of each other. Okay, similarly you can see that these two branches are mirror image of each other, so these two branches have same potential difference and same current flowing through them. All right, so this is the circuit number 2 and these are the 2 points, okay, x and y, across which equivalent resistance is to be calculated. So let's join these 2 points. Now you can see that this straight line divides this entire circuit into 2 equal parts. Okay, the lower half is the mirror image of upper half. Okay, these two are exactly equal. Okay, so we can say that this circuit has a first plane of symmetry or horizontal plane of symmetry, or it is also known as the parallel axis of symmetry or folding axis of symmetry. Okay, so in that case the mirror image points are at equal potential, that means these 2 points are at equal potential. Similarly this point is the mirror image of this point, so these 2 points are at equal potential, these 2 points are at equal potential. Okay, and the mirror image branches have same potential difference and same current flowing through them. Okay, so this branch is the mirror image of this branch. Okay, so if a current I flows through this resistor in this direction, then same current I flows through this resistor. Okay, and the potential difference across this resistor is equal to the potential difference across in this resistor. Okay, similarly these two resistors are the mirror image of each other with respect to this straight line. So let's say a current of capital I flowing through this resistor in this direction, then a current I will flow through this resistor. Okay, as these two resistors are mirror image of each other. Okay, and these two resistors have same potential difference and same current from them. Okay, the three things. Okay, mirror image points, that means the point which are the mirror image of each other with respect to this straight line are at equal potential. This is the point number 1. Then point number 2 says that the mirror image branches, that means those branches which are mirror image of each other with respect to this first plane of symmetry, they have same potential difference and same current flowing through them. Okay, so in that case what we can do, that we can join this point with this point and join this point with this point. That means we can fold this lower part of the circuit into the upper part of the circuit. Okay, so first of all let's see the step by approach. So here it is the step by approach. Okay, so step number 1, identify the 2 points across which are equivalent, that means equivalent resistance is to be found. Okay, this is the step number 1. You have to identify the points across which are equivalent is to be calculated. Okay, now in step number 2 what you have to do, you have to draw a straight line joining these 2 points. Okay, so in step number 2 you have to draw a straight line joining these 2 points. Okay, and you have to think of a plane. Okay, think of a plane passing through this line. Okay, you have to think a plane which passes through this straight line. Okay, then in step number 3, if this straight line or this plane divides the circuit into 2 equal half. Okay, if this straight line or plane divides the entire circuit into 2 equal half, then in that case we can say that there is first plane of symmetry, or we can say that horizontal plane of symmetry, or we can say that parallel axis of symmetry, or that is also known as folding symmetry or horizontal axis of symmetry. Okay, so if a circuit contains first plane of symmetry, then about the first plane of symmetry, that means considering the first plane of symmetry as the mirror, we can say that the mirror image points are at equal potential, mirror image branches have same potential difference, and the mirror image branches have same current flowing through them. Okay, these are the 3 very important points. Okay, so here is the circuit. let's say we want to find out the equivalent resistance between these two points, point A and point B. Okay, so step number 1 says that identify the points across which equivalent resistance is to be calculated. So these are the point A and the point B. Okay, this is the step number 1. Okay, then step number 2 says that you have to draw a straight line joining these two points. Okay, that means here it is the straight line joining these two points. Okay, if this straight line divides this entire circuit into two equal halves, okay, then we say that this circuit contains first line of symmetry. As you can see that this straight line dividing this circuit into two parts. Okay, the lower half is the mirror image of upper half. Okay, these two halves are exactly equal. So you can say that this circuit contains first plane of symmetry. Okay, and if a circuit contains first plane of symmetry, then in that case we can say that the points which are mirror image of each other, this point and this point, these are the mirror image of this mirror image of each other with respect to this straight line. Okay, so these mirror image points are at same potential. Okay, let's say the potential of this point is V, then this point will also have a potential of V. Okay, this is the point number 1. That means the points which are mirror image of each other with respect to this straight line have same potential. Okay, then point number 2 says that the mirror image branches, that means the branches which are mirror image of each other with respect to this straight line have same potential difference and same current flowing through them. Okay, so this branch is the mirror image of this branch, so this branch have same potential difference and same current flows through these two branches. Okay, so let's say a current I flowing in this branches, then same current I flowing in this branches. Okay, similarly as you can see that these two branches are the mirror image of each other. Okay, so they have the same potential difference across them and same current flowing through them. Okay, if a capital I current flows in this branch, then capital I also current flows in this branch. Okay, so in this case what we can do is we can fold this lower half into the upper half. Okay, we can connect this point with this and this point with this. Okay, as these two points are the mirror image of each other. So what we can do, that is the point A, that is the point. Okay, so you can connect this point with this. Okay, so in that case what we can do, so you can draw this resistor here also. Okay, this one is the first resistor and we can put this resistor over this. Okay, so it will be something like this. So this one is the resistor and this is its mirror image. Okay, so we can put this branch over this branch. Okay, so there will be two branches. Okay, similarly you can put this branch over this branch. Okay, this branch can be put over this branch. Okay, this is the folding. Okay, that means we fold this lower part into this upper part. Okay, so now these two resistors are in parallel and these two resistors are in parallel, and now this circuit can be solved. Okay, so that's it for this video. Thank you for watching this video.